So this is a problem where we are looking at the impact of the specific heat capacity. This is a property of all materials, the specific heat capacity on the temperature of air when you supply some heat energy to it. Right? So obviously there are practical applications in ventilation. So let's take a quick look at the problem. So we know that if you supply some energy, heat energy to a material, to a mass of material. The material can be a solid or a liquid or a gas, it doesn't matter. The temperature will go up. How much does the temperature go up? Well, that depends on the specific heat capacity of the material. And if you're talking about a gas like air, along with an increase in temperature, if you keep the pressure the same, the density will go down. It'll become less dense. Right? It'll occupy a larger volume. Well, that's a property of gases. So here we are looking at a problem where you have 5 cubic meters of air per second going through a large vent, and you're heating this air, and the temperature of the air goes up, and the volume that it occupies also changes because the air is now warmer, and the density has changed. So how do we put some numbers here? So what we would like to see is how much does the temperature change, and what is the impact on the volumetric flow rate of air as it goes through. So if you look at what happens to this mass of air as it is going in, we are talking about five cubic meters of air at and let's assume about 20 degrees Celsius. And at that temperature, we can look up the density of air at that temperature. It's about, say, 1.25 kilograms per cubic meter, which gives us 6.25 kilograms of air going through every second. So we know the mass of air going through every second. And this is important because we want to see how much the temperature will change. And in order to understand that, we need the mass of air that's going in 1 second. So in 1 second, if you supply 1 kilojoules, 1000 joules of energy, which is the same as saying 1 kilowatts, so 1 kilowatts of power is 1000 joules per second. Then what's going to be the temperature change? Well, you can find the temperature change by dividing this heat input by the mass and the specific heat capacity. So if you do that, you get a temperature difference of 160 degrees Celsius, and since 20 degrees is the initial temperature, now the final temperature is 180 degrees. Right? At this temperature, of course, the density has changed, and now it's become less dense. And so, since the mass is the same, the same mass is going through, that's not going anywhere else. It's going through the vent. It's now occupying a larger volume because the density is lower. What's this volume? Well, you can calculate the volume by dividing the mass that's going through by the new density. So you see a volume of 8.33 cubic meters per second. And essentially, you have calculated whatever was asked for in the problem. And if you draw a graph taking different values of volume of air going in per second, then you will see how the temperature changes and how the volumetric flow rate of warm air changes as well. So you see, if you push in 5 meters cube per second of cold air and heat it up, the temperature goes up. If you push in a great deal more cold air with the same heating source, right? Now the temperature is not going to go quite so high. It will still go up, but less so. And the graph reflects this case. And the same thing with the